It looks like folks have, the filtering in has sort of tapered off a little bit. Let's go ahead and get started. Good morning, everyone, or good afternoon or evening, depending on what time zone you are in. Welcome to the QChem webinar. We're really excited to have all of you here this morning, and we are also very excited to have Anthuan here with us to talk about some of his work with couple cluster in DFT embedding, both his implementation of that in QChem, and then also the application of that to study the polarizabilities of solvated organic molecules. So first, a little bit about Anthuan. He is a postdoctoral researcher in the group of Professor Stopkowitz at the Universitat des Saarlands. He obtained his PhD in 2025 from KU Leuven, where he worked with Professor Thomas Yao on projection-based quantum embedding methods. His ongoing work includes some electronic structure theory for the description of bound systems and electronic resonances, projection-based quantum embedding methods, and ranges from those sorts of things to like molecular docking and things like that as well. And in fact, he also recently implemented it's newly available in QChem 6.4, this projection-based couple cluster in DFT embedding that he's going to be sharing a little bit with us about today as part of his webinar. So we're really excited to have him here. One quick logistical thing before we get started. If you have any questions during the duration of his talk, please go ahead and post them in the chat or the Q&A at the bottom. And we will have a Q&A section at the end where he will get around to answering some of your questions. So thank you so much. Anthuan, we're so excited to have you here this morning with us. And without any further ado, I will go ahead and hand things over to you.
So I can share my screen now.
Yes, absolutely. Perfect. Thank you.
So thank you, Shan, for the nice introduction, and thank you for everyone for being here. Yeah, today in this webinar, I want to talk to you a bit about my work in coupled cluster intensity functional theory embedding for the study of static polarizabilities in aqueous environment. This is a work that I carry out during the end of my PhD at KU Leuven, and I really like the result that we got. So I hope that you are also get to enjoy the presentation. So chemistry has been through most of its history, as we know, an experimental science. However, nowadays, this is no longer the case. Theory and experiment now work together, and this collaboration has led to a revolution in many different spheres, from material science, electronics, astrochemistry, agriculture, drug design, and many others. However, as we know, computational calculations are usually restricted to isolated systems in the vacuum or gas phase, as we call it. However, we know that most chemical processes take place in condensed phase, where the interaction with the environment play a critical role in the process that we are trying to describe. However, when we want to use accurate quantum chemistry methods, we usually face the problem that these methods become unfeasible, either because they take too much time or because our computers don't have enough space to store all the information that these methods require. So what do we do as computational chemists? We use models for representing the environment and these condensed phases. I think we can group the environments in three big categories. First off, the most simple of all of them is continuum models, which basically reduce all the information of the environment to one property. Usually it's the electric constant. Then on the other side of the spectrum, we have atomistic models, which include all the atomistic complexity that condensed phase have, but then usually need to rely in using methods that are not based in quantum mechanics to describe the environment, because this is not feasible right now for our current hardware. In the middle between these two are clustered models, where basically what we do is just to choose which molecules of the environment have relevant interactions with the system of interest, and then just construct these sort of clusters to actually use methods that are more powerful than what we will able to do when we have a fully atomistic representation. So how to choose the correct model? Well, this is usually an act of balance where computational chemists need to evaluate the cost, the accuracy of the model, and the method that they want to use. If we want to use very accurate methods and include the effects of the environment, usually we rely on what is known as multi-scale approaches, where basically we separate our system into two parts. The active part, or high level, the one that we want to use with our very accurate method, and a low level part, which is usually where we put the environment and where we use a method that has a lower computational cost. This sort of division between active fragment and environment is what leads to what is known as embedding method. And if you choose both for the high level and the low level methods that are based in quantum mechanics, this is called quantum embedding. There have been different realizations of quantum embedding through the years, and you can look most of this on the literature. But in this talk, I'm going to focus my attention in what is known as projection-based quantum embedding. Here, I want to just go through the motion of what a quantum embedding, projection-based quantum embedding calculation looks like. Specifically, it's Kuznaga variant. And for that, let's just imagine that we have this type of cluster of one organic molecule surrounded with 5 water molecules. The first step of a projection-based quantum embedding calculation is to do a DFT calculation of the entire system. DFT, density functional theory. So it's a very good way of getting a first approximation of the whole behavior of the system. And in that way, we compute the whole system with it. And then after DFT has been converged, we can localize the occupied molecular orbitals. These occupied molecular orbitals, the ones that have electrons on them. And we can separate them into two parts. The fragment A, the active part, the one that we're actually interested in, and the environment. Why we do that? Because we want to do a second calculation where we just study the behavior of our active fragment, right? So for that, we construct, after this division, what is known as an embedding potential. This embedding potential basically carry out the interaction of the active fragment with the environment, and it is included in what is known as an embedded Fock matrix, which have the expression that I present to you here in the slide. But there is an extra step that needs to be taken, because what we want is to freeze the orbitals of the environment during this second calculation, but carry out its information. So we are already carrying out the information using the embedding potential. But to assure that the orbital of the active fragment doesn't mix again with the orbital of the active part, we need to ensure that they remain orthogonal during the second calculation. And for that, we use what is known as the Kuznaga matrix, which is basically an effective Fock matrix, which has the expression that I present to you here in the slide, which includes a projector that assures that the orbitals of A remain orthogonal to the orbitals of the environment during the whole calculation. With this, we carry out a second calculation because we are doing wave function in DFT embedding. This second calculation is Hartree-Fock, but it's also possible to do DFT in DFT embedding. But yeah, for the case of this work, we do a second calculation, which is in this case Hartree-Fock. And then with the result of this Hartree-Fock that is carried out using this effective Fock matrix, we then can give it the result as input for any high-level method that we want, either MP2, coupled cluster, equation of motion coupled cluster, or whatever method you have of your preference. The final expression for the energy of our system will then look like the one that I presented to you in the slide. You see that we have a term that accounts for the high-level part of the energy, while we have the second and third terms are there to compute the energy of the environment, but also to avoid double counting the energy of the active part. The last term in the energy expression is what actually includes the energy that comes from the interaction between the active fragment and the environment. Okay, so now that we know how the projection-based quantum embedding method works, I said in the beginning that we want to use it to study polarizabilities. And why specifically polarizability? Well, let's first introduce what polarizability is. If we have a charge distribution in the presence of an external electric field, we know that the charge distribution will separate and then will appear an induced dipole moment. Polarizabilities are defined as the strength of this induced dipole moment, which we can also define it using this derivative. And the key thing here is that they are very important to understand and predict intermolecular and molecule field interactions. On top of that, from an experimental point of view, it has been shown that polarizability influences material properties, Raman intensities, and solvatochromic shift. So you can see why there is a lot of interest from the experimental side to obtain and have very accurate reference values for the polarizability. In the case of from the theoretical point of view, polarizabilities have been used to estimate dispersion coefficient and dispersion correction. So we know that these are things that are used in, for example, DFT for the construction of functional. So we want to have reference values, again, that are very accurate and can be used for this. So in the framework of response theory, a given element of the polarizability tensor will have the expression that I present to you here in the slide for the static limit. And it is useful to introduce two quantities, the isotropic polarizability, which is basically the mean of the diagonal elements of the polarizability tensor, and the anisotropic polarizability, which basically tell us how the different elements differ between themselves. These two quantities are independent of the orientation between the molecules, and in our case are very useful because they allow us to compare the polarizability, the tensor in different clusters. So we will go back to these quantities later, but the idea here is that in a full excitation space, and if you carry out a normal calculation using this formula to obtain the polarizabilities, what you need to consider is both the excitation that come from your active fragment A and from the environment B. However, as we say, in a standard projection-based quantum embedding calculation, the orbitals of the environment are frozen during the second calculation, during the high-level calculation. So this is okay if you only want to describe the central fragment. And in this work, we actually study how the central fragment, the polarizability of the central fragment change, which is the inclusion of more water molecules. And one of the first things that we saw is that the polarizability of the organic molecule that we put in the center of the cluster didn't vary a lot with the inclusion of more water molecules. It varies only slightly. And also was very interesting to check that our results kind of contradict previous theoretical studies that were done with a lower level of theory, emphasizing the importance of including correlation in this calculation. But yeah, going back to the main topic of the talk, we see that, okay, if you want to describe the central fragment, this works. However, if you think about it from an experimental point of view, you cannot measure only the polarizability of a molecule in a solution, right? You measure the whole thing. So the contribution from the environment cannot be neglected, and you kind of want to compute the supermolecular polarizability, the polarizability of the whole cluster. You can easily see that if in this summation, we are ignoring all the contribution from the environment, which will usually be more orbitals, more excitations than just the ones from the active part, then this leads to a huge underestimation of the supermolecular polarizability. So the question that we posed during this work and what we wanted to answer is, how can one include the contribution of the environment to calculate the supermolecular polarizability using projection-based quantum embedding? Well, we actually came up with two ideas for doing this. We proposed two methods. The first then is the iterative embedding approach, which actually, as Shannon said, is implemented in QChem, and you can use it in QChem 6.4, which the idea here is basically that you can estimate an element of the polarizability tensor adding up the contribution of each individual term. What we are doing here is basically iterating which molecule in our cluster is treated at the high level. This has the advantage that by the end of the calculation, you have achieved a high-level description of the entire system at a fraction of the computational cost of doing a full CCSD calculation, because of course, doing each of these at the high level is cheaper than doing a full CCSD calculation for the entire system. Also, that we are using analytical derivatives because we can use it for each one of the elements in the cluster. And on top of that, because we are using analytical derivatives, we are saving computational resources compared that if we were doing this numerically. The drawbacks of this approach are, well, basically that right now the implementation neglects orbital relaxation, which means that, yeah, the effects of the orbital relaxation is not included in the results, and this we will see later that have an effect in the quality of the result that we obtain. And the other thing is that because we are iterating over which fragment is the high-level part, there is no way for us to ensure that the orthogonality is preserved between the different high-level fragments. So this is another source of error that can appear in this method. The other approach that we propose is to just use a finite field approach, which basically we went back to the actual definition of polarizabilities. And what we obtained was that by using the numerical derivative, we don't have a high-level description of the entire system, only of the active fragment. Second, well, as I said, we are using numerical derivatives, and therefore the computational cost increase. However, the advantages of this approach is that it accounts for orbital relaxation because the field is present from the beginning of the calculation, and therefore the effect of the field on the orbital is being taken into account. On top of that, the orthogonality is preserved because we only do one projection-based quantum embedding calculation. So we don't have to worry about the different fragments at the high level not being orthogonal to each other. So we are eliminating this possible source of error. So we tested these two methods against CCSD, and so we did a full CCSD calculation for the entire system and compute the isotropic and anisotropic polarizabilities with the ones obtained with our two approaches. And we also compare the result with DFT, because if DFT performs better, what is the point of any of this, right? So first, I present to you the result for the supermolecular isotropic polarizabilities. And as you can see, there is an excellent agreement of the iterative method with CCSD, regardless of the density function that you use to describe the environment. And here is where iterating over the different parts and having a high-level treatment of the entire system comes to play, because you can see that even PVE, using PVE for the environment, is enough to get a very accurate description. You have less than 1% of error in all these cases, and you outperform DFT and the other approach that we propose for isotropic polarizability. In the case of the finite field approach, we observed that it also outperformed DFT in most cases. However, the main problem here is that it does depend the quality of the results of which functional you use to describe the environment. You see that also DFT also suffers of this, and these two are related in that regard, because the finite field approach has a high degree of DFT component in final results, because you are not including everything in the high level part of the calculation. But we were very happy to see that the iterative method produced these very good results compared with CCSD at a fraction of the computational cost. In the case of anisotropic polarizabilities, then this is not the case. The iterative method doesn't perform as well. And you can see that it's usually even outperformed by DFT in most cases. But this is because we have pinpointed the source of these errors to the lack of orbital relaxation during the calculation. This is something that we are working it right now, so including these effects. You can also see that, for example, the finite field approach produces very good results when you use the correct functional, because it does include orbital relaxation. Also, you can see also that DFT is not that bad either. So in summary, these two methods can be seen as complementary to each other, you can use the iterative approach if you are interested in isotropic polarizabilities, and you can use the finite field approach if you want to compute anisotropic polarizability. So both of these methods are viable, and you obtain the result at a fraction of the computational cost that full CCSD will be. However, we didn't stop here because, as I said in the beginning, we want to study systems in condensed space, specifically in solution. And we know that just measuring some clusters is not enough to get the full picture in solution. You actually need to explore the whole computation, the whole configurational space. So to do that, in the literature, there has been reports that basically use molecular dynamics to get the different configurations that are relevant for a given system. And what people do is basically to do some sort of double embedding approach where you have this QM region embedded in molecular mechanic region. But in this work, we went in a different direction. We use what is known as the multiple minima hypersurface approach, where basically we put our solid molecule in the center of a cubic box with 50 water molecules surrounding it. We generate 200 random configurations, and by doing this and computing their energies using a semi-empirical methods, in this case PM7, we are able to construct a canonical ensemble and use statistical thermodynamics to obtain a Boltzmann population and extract the relevant configurations of a given system in solution. These relevant configurations were then studied using our embedding approach, and we basically extract the clusters, and we basically took a solute plus the 9 closest water molecules. You can see that this size of system is already something that is not manageable by full CCSD. So there is already where our method can give us more insight. We did this for 10 different organic molecules, and here I present to you the results that we obtained for the different configurations. You can see that the standard deviation is very small. So we choose the mean as a way to describe the behavior of the different systems among different configurations, since the small standard deviation is a good proof that this is a good descriptor. If we look, for example, at the hydrocarbon, we can see that our method is able to reproduce something that is very well known, that is an increase of the polarizability with the molecular volume. And also, we also study the aldehydes and the hydrated counterparts. And you can see that in solution, the hydrated form is always approximately 8 atomic units higher than the aldehyde form, which explains why it's the favorite form in solution. So we were happy to see that our method is able to reproduce these trends that are very known by experimentalists. And when we look at the anisotropic polarizability, again, the standard deviation is very small, but it's a bit bigger than in the case of the isotropic one. But the mean is still the descriptor that we choose to study the behavior among different configurations. And here we observe that there is a higher anisotropic polarizability in unsaturated molecules, which is to be expected because, doubles and triple bonds are more anisotropic than single bonds. And this is also the case for the aldehyde forms compared to the hydrated counterparts. So we were happy to see that our method is able to reproduce these very known trends in solution. And we took this as a proof that it can describe the behavior of organic molecules in solution correctly. Before finishing, I would like to present some new developments that we have. This is not published yet, but what we went through after going to the ground state polarizability, we went to study excited state polarizabilities. And I have to mention that this works, the embedding specifically, if you are interested in localized excitations, because if not, you cannot separate the contribution from the two systems. But if it is the case, and you can do this separation, then you can basically approximate the polarizability as, you compute the high-level part of the excited state polarizability using, for example, equation of motion coupled cluster, and the rest of the solute, you you just iterate over them, but just using ground state, just computing, ground state polarizability. This is something that is actually also implemented in the 6.4 version of QChem, and we are trying out its performance. As you see here, the preliminary results show that the errors are bigger than for the ground state. However, the omega B97 family seems to be the best performing functional. We obtain results for the isotropic polarizabilities and for the anisotropic polarizabilities. And we also agree that the good performance for the isotropic polarizability of PBE and B3D is possibly due to some error cancellation, but because if you look at the anisotropic polarizability values, you can see that they are way, way off. But in general, this is a very exciting direction that we want to keep looking on, because we think there is very promising way to obtain cheap excited state polarizabilities, which are even more expensive than the ground state one. So we think, yeah, this approach can be very promising, obtain very good results. In conclusion, I hope I could have shown you that CCSD-in-DFT embedding is a first principle approach to compute ground state static polarizabilities in condensed phase. This work was the first report of the computation of static polarizabilities using projection-based quantum embedding. We also showed that there is little variation in the polarizability of organic molecules when you start to include water molecules in the clusters. And we present two complementary approaches for reliably computing ground state supermolecular polarizabilities. Also, we demonstrate that combining this method with the multiple minima hypersurface approach for the exploration of complex configurational space is a reliable way of obtaining trends and properties of molecules in condensed phase in solution. On top of that, the iterative equation of motion CCSD-in-DFT is a method that is promising for the study of excited state polarizabilities. Before finishing, I would like to acknowledge all the people in the group of Professor Thomas Jagau at KU Leuven, where I did most of this work and my PhD. Also the funding agencies, QChem, and in the University of Saarland, to my current supervisor, Professor Stella Stokowitz, for all her support, and of course, you for your attention. I will be happy to answer any questions.
Wonderful. Thank you so much. That was a great talk. And as you said, if anyone has any questions, there is a chat box where you can post them. We'll give folks a minute to post any questions they might have. Mm-hmm. Okay. Well, if nobody has any questions, can you go back a few slides, please, to the excited state ones? I just have a quick question, and you may have covered this and I missed it, but it's the next for the anisotropic ones.
Okay, sorry.
So it's interesting to me that the Minnesota functional and CAM-B3-LIP seem to do better for the second case than the omega B97s. Do you have any indication of why that might be the case?
So, because these are just preliminary results, this is just one configuration. So our conclusion in general, and this is also something that we also observe when we look at in the ground state, is that you need to actually look to more configurations to get like a whole picture of how a function actually perform. Mm-hmm. But in general, the omega B97 X family tends to overall perform better. It can be a specific case where it doesn't work as well, but it's more like when you cover a high range of systems, then it averages to be better. So here we are only presenting one given cluster, and it was the case that the Minnesota and Cambridge relief perform better in this case. But I think in general, the results are more consistent if you use the omega B97X family of functions.
Okay, awesome. Thank you. And I know that you said that they were generally, I think you said this during the talk, which is why I was wondering why the numbers seemed, yeah, okay, that makes sense. Thank you.
Also, an interesting thing that we observed for the excited state that we didn't observe for the ground state is that if the functional that you choose does affect the quality of the result, which is something that we didn't observe for the iterative method for the ground state. So this is also a direction where we think it will be very interesting to see why this is the case.
Absolutely, yes. Thank you. So it looks like we've got a couple questions over here. One person says, thank you for this presentation. How straightforward is it to request such embedding calculations through QChem? What options should be specified?
If you just want a standard embedding calculation, is pretty straightforward. The iterative embedding approach, if you go to it, it's actually updated on the manual. So you there have an example of how you can run this type of calculation. You basically just need to turn on the keyword for that and just select from which molecule you would like to start. Basically, if you want to do the default calculation, you just put 1. So it starts from your first molecule and it will iterate over all of them. But in case the calculation fails while you are in the third molecule, you can just start from the 4 and then combine the results. This is also, the code is flexible in that way that you can also do it like that. But if you go to the manual section, the examples there, I think they are very clarified.
Okay, thank you. And I'll try to post the manual section in a minute. But we've got a lot of questions, actually. This is exciting. So one person asks, what about obtaining free energy profiles with your techniques? Is that possible in your embedding approach?
I think there is a direction where you can go through that, but then it will require some, I think, extra implementation just because the free energy usually requires that you compute some entropy at this level, right? So I think it for sure will be interesting. And I know that the multiple minima hypersurface approach gives you a free energy profile, but you will just have it at the semi-empirical level. You will not have it at this level of theory that we're using. So we are kind of going through the potential energy surface and looking at these energies by means of this, but only at this very superficial level, I would say. But I think more work will need to be done if you want to go in that direction.
Okay. Thank you. And then, is it possible to apply CC-in-DFT embedding method?
I think, I mean, theoretically, it should be possible just if your active region is just the one where you want to put your active space, right? The thing. But there is no problem in doing that from the embedding side because it is for the high-level method, it is not different than just doing a Hartree-Fock calculation. So it depends. I think the implementation is not there, that's for sure. So because you need to enable this definition of the active space within the embedding approach. But I don't see a reason why it will not be possible after you localize the orbital that you set up an active space. It will be for sure be something very interesting to try how it performs.
Nice, yeah. Sorry.
The good thing of projection-based quantum embedding is that you kind of can add whatever flavor of post-Hartree-Fock method that you want on top of that, and it is the post-Hartree-Fock method tends to be blind to the low-level part.
That Makes sense.
It is why is the method that is usually combined with, like, you see CCSD-in-DFT, EOM CCSD-in-DFT. For the other embedding approach, you basically always kind of see DFT in DFT with different functionals. But because you can have this separation, the projection-based quantum embedding is the one that allows you for even go more accurate within embedding approaches.
Okay, thank you. And then we have another question, which is, thank you for the interesting talk. Could you please comment on the computational saving passing from CCSD to PBQE for the iterative and finite field approaches?
Yeah. So I don't have like hard numbers, but I know from my experience and when we did it for the paper that, for example, if you want to run the cluster of these small, or because they are, I would say they are not very big, small organic molecules and water, it will take the full CCSD calculation will take you a week, while in the embedding you get the results in a day. So you can see that the savings are very considerable. And what we saw for the excited state case is that if you know how excited state polarizabilities are computed, you know that this entails even higher computational costs, and there the savings are way, way more. But that's why we are interested in see if we can manage to make them work, because or work better than how they are performing right now. Because I mean, even for the without any embedding, we know that excited state polarizabilities are tricky to get right. So yeah, but the savings, the ones I can say for sure, for the ground state, you go from 1 week to 1 day. I would say that all these calculations were done using augmented triple zeta basis set. So this is already like a big basis set for this type of systems. So it is a huge amount of savings. Also from the memory part, because you are freezing a lot, so there's a lot of things that you don't need to have at all times.
Okay, thank you. And I've also just posted, for those of y'all who are interested in how to run these calculations, I've just posted the manual section in the webinar chat, if anyone wants to look into that at all. And then I think we have 2 more questions. So one is on the excited state slide for polarizabilities, you mentioned EOM CCSD with the various treatments. Is the DFT just used for the environment then? This person is just surprised that the difference is so large for just the one water molecule. Yes.
Yeah. So yes, the DFT is just used for the environment, but you need previous reports of the use of embedded, not even for polarizabilities, but also for excitations, have shown that because we didn't want to have to put the molecules in a given position. So we generated the cluster that we choose randomly, right? Or as randomly as we can. And you can end up with configurations where there is an interaction between your environment and your excited state. And if it's the case, it is demonstrated that this can lead to the failing of the embedding. So we suspect, that's why we wanted to make a bigger study, that this could be one of the reasons why, because you're already working in an excited state and then you are adding up overexcited state. And we know that excited state can be affected way more by how close or are the orbitals of the environment molecules, basically. We were also surprised that the difference were so big, but at the same time, you can see that even the EOM CCSD values are very big. If you compare it to the ground state polarizabilities, and then you compute the values just go like these results are in Hartree, and you can see how big these numbers are even. So there is a lot of room for variation here, and you see that here instead I presented in percent because I think they give a better picture of how much they are changing in the end.
Okay, thank you.
But yeah, we were also this is a good question because we were also surprised of how much this have an effect.
Mhm. Very good. That makes sense. Yeah, thank you. And then we've got one final question, which is, thank you for the interesting talk. Could you please comment on the sorry, this is a duplicate question that was posted in the Q&A in the chat. So in that case, I guess that was the last question. If anyone has any lingering questions, or you wake up in the middle of the night tonight and realize, oh, darn it, I forgot to ask something, then we will have a thread on the QChem forum where you can ask any additional questions that you might have. Or if you're watching this on YouTube later, then you can post in the forum thread there. And this will be posted on YouTube within about a week or so. And yeah, so thank
And
you
you can
again.
also,
Yes.
sorry to interrupt, you can
No
also
problem.
look at the paper is already published for the first, almost the whole talk. So you can look into that, and there you can also find my email. So you can also write me if you have any question about how to use the method, or yeah, any questions in general.
Yeah,
I
thank you.
will be happy to answer any question.
Yeah, thank you very much. And it's an excellent paper. I've seen it before. So anyway,
Thank you.
so thank you for being here today and for the excellent talk. And I hope everyone has a wonderful rest of their day. Take care, everyone.